Now we shall be taking a look about the self-inductance that is occurring in a given solenoid. So, self-induction in a solenoid, right? Let us see that how the solenoid looks like. The solenoid looks like this is, say, the number of turns, like this. Okay. Now in the solenoid, obviously there will be a current, this I, right? And also we can say there are n number of loops, right? And we could denote A as the area of the cross section, right? As we have seen in the previous lecture that R was the radius of a plane coil, so the area would have been pi r squared. This area is that area over where the magnetic flux or the magnetic, like the B, will be occurring. Okay. Now we could take over here that this is I, the current, and this B, the magnitude of B. It will be equal to, in this scenario, mu naught Ni divided by L, right? Where the L is the length of this solenoid, right? So, as by the formula of the self-induction, we can write that phi is equals to Li, as we have seen before. So we can write this phi as NBA cos theta directly, as now we have known that phi equals to NBA cos theta, where it has got n number of loops for n number of terms. So it will be NBA cos theta equals to Li. Now the theta in this scenario will be equals to 0, because as we have seen earlier that the B and the A vector both lie in the same line. So the angle between them will be 0. So if the angle between them will be 0, so cos of 0 will be equals to 1. So we can write it as simply as NBA equals to Li. NBA equals to Li. Right, and what we could write B as this one. Okay, so we are going to replace B with this term. So it will come out to be N multiplied by mu naught Ni divided by L multiplied by area equals to Li. Now also carefully, this I will get cancelled to this I, right? And if it happens as such, we can write this term L as equals to mu naught N square multiplied by the area divided by the length. So over here, the self-inductance of a given solenoid will be equals to mu naught multiplied by the square of the number of turns or the number of loops multiplied by the area of the cross section of this solenoid divided by the length of this solenoid, right? So this is about the self-induction of a solenoid. Now, as we have seen that the self-induction actually it opposes or it takes much time to get the current increased to its peak value. So how we can reduce that, right? The method to reduce it is known as non-inductive wiring. If we could do as such of non-inductive wiring, then it will be lesser. Let us see it how. A coil, first of all, is coming like this, right? And afterwards, again, now it is joined as such that it goes by like this. Okay? Let this is a point from which the current was coming and it is connected over here, and this is another point to where it is going. It is now connected over here, right? And between these two there could be, say, a battery. If this was not the case, the opposing EMF would have been there, the self-induction would have been there, the self-inductance would come into play, and subsequently the time would have wasted in getting the current rise to its peak. Now this is a kind of non-inductive wiring. Why it will not oppose, let us see. But yes, the phenomenon of the Faraday's law or the Lenz's law will remain as it is. We cannot change that, but we have designed something so that the effect of this, say, the wires of these red lines now will be cancelled out by the effects of these black lines. Obviously, they are the same line. First of all, they are going via this red line, and at the end of this red line, they are now coming back via this black lines, right? Obviously, they are same lines. For your better understanding, we have done like this, right? So, see here, if the self-inductance, this is like this, so the current will flow like this, a self-inductance current will flow like in this direction. We are going to make only the self-induction currents, right? So this will be in this direction, or basically we could start it from over here, in this direction, in this direction, in this direction, in this direction, and again in this direction, in this direction, in this direction, and what? Right? Now it is opposing. But for these black lines, observe minutely, this will just be the opposite. So the induced current or the self-induced current due to these, say, red lines are now opposed by the black lines. As you could see, the arrows are on the opposite direction, right? So this is the methodology of non-inductive wiring. If we could make a device, or if we could make the wiring as such that the opposite induced EMF of one coil would cancel out or negate the induced EMF of the other coil, right? And likewise then we could minimize this self-induction within a coil itself, right?